In this lecture, let's discuss the KKT condition. Let's consider an optimization problem in the standard form. The objective function, the objective is to minimize a function fx subject to inequality constraints and equality constraints. Here, the gx and hx are vector functions. Therefore, we have multiple inequality constraints and multiple equality constraints. So the gx can be written as, the inequality constraints can be written as gix less than or equal to 0, I from 1 to m. Let's assume we have m inequality constraints. Then the equality constraints can be written as hix is equal to 0, I from 1 to p. So let's assume we have p equality constraints. The basic idea in the Lagrangian duality is to take the constraints into account by augmenting the object functions with a weighted sum of the constraint functions. Then we define the Lagrangian L. Then L is a function of x, lambda, and v. Lambda and v are called do variables or Lagrange multiplier vectors associated with this optimization problem. So the definition of the Lagrange is like this. We have the fx, that's object function of the optimization problem. Then we have lambda transpose. So lambda is a do variable or Lagrange multiplier times gx, the inequality constraints, plus v transpose times hx. So v is another do variable or Lagrange multiplier vector. So hx is the equality constraints. The h lambda transpose gx can also be written as a sum I from 1 to m lambda I gix. So lambda I is referred to as the Lagrange multiplier associated with the S inequality constraints. And v transpose hx can be written as a sum I from 1 to p vi hix. Similarly, vi is referred to as the Lagrange multiplier associated with the ith inequality constraints. Then let's define the Lagrange do function or just do function g. G is a function of lambda and v. So the definition is like this. The infimum of f x lambda v with respect to x. Since the do function g lambda v is a pointwise infimum of a family of affine function of lambda and v. So therefore, the do function is a concave function. Assume we find the optimal solution of this optimization problem. Suppose we know that the optimal solution is x star and the minimum value is p star. Then the do function g lambda v gives lower bounds on the optimal value of p star. So therefore, for any lambda greater or equal to 0, and any v, so the g lambda v is always less than or equal to p star. Since the g lambda v is the lower bound of p star for any lambda is greater than 0 and any v. Therefore, we are interested in finding the best lower bound that can be obtained from the Lagrange do function. This leads to the optimization problem: maximize g lambda v subject to lambda is greater or equal to 0. This problem is called the Lagrange do problem associated with the original optimization problem. In this context, the original problem, optimization problem, is sometimes called the primal problem. Then the optimal solution from the do problem, so lambda star v star, are referred to as the do optimal or optimal Lagrange multiplier. So no matter the primal problem is convex or not, the do problem is always a convex optimization problem. Let's use D star to denote the best value of the Lagrange do problem. So that is G lambda star V star. Then by definition, so we have this inequality. So D star is always less than or equal to P star. So the D star is the best lower bound on P star. This property, it is called weak duality. If the equality holds, that is D star is equal to P star, so that is the optimal duality gap is 0, then we say that strong duality holds. When the strong duality holds, we have a very important conclusion. So this is also called complementary slackness. So the lambda is a do variable, is the optimal do variable. Then the x is the optimal solution, primal optimal. So the lambda is the do optimal. Then we always have lambda I times gi is 0. So in other words, when the S inequality constraints is inactive, then we must have lambda I star is 0. When the S inequality constraints is active, so we must have this lambda I star is positive. Since X star is the primal optimal point, therefore it must satisfy all the inequality constraints and equality constraints. Since lambda I star is the do optimal point, it also needs to satisfy the constraints. Then this is the complementary slackness condition. So last we know, so that the X star minimize the lambda, the L, X, lambda star, and V star over all X. It follows that the gradient of the Lagrangian at X star must, the gradient of the Lagrangian when the lambda is lambda star and V is V star must vanish at X star. So in other words, if we take the gradient with respect to X, then let X to be X star, then it must be 0. So therefore we have this condition is a gradient of the Lagrangian L with all the primal, optimal, and dual optimal points. So all the conditions together, so they are called the KKT condition. In summary, we have the following conclusions for non-convex optimization problem. So in other words, the original optimization problem is not convex. We have this conclusion for any optimization problem with differentiable objective and constraint functions for which strong duality obtains, any pair of primal and dual optimal points must satisfy the KKT condition. So therefore, the KKT condition is a necessary condition for the non-convex optimization problem for the primal and dual optimal points. Then for convex optimization problem, in other words, the original optimization problem is convex. Therefore, we have this conclusion for any convex optimization problem with differentiable objective and constraint function. So any points that satisfy the KKT condition are primal and dual optimal, have zero duality gap. So in other words, for convex optimization problem, the KKT conditions are not just necessary, they're also sufficient. So in other words, we can solve the KKT condition to find the optimal primal points and optimal dual points. The KKT condition can also be used to verify is a point X is optimal or not.